Good morning. This is Todd Coburn with Cal Poly Pomona with the Aerospace Structures Series Part 2 on the practical analysis of aerospace vehicles. Today we're going to be looking at Lecture 16a, which is going to deal with weld fatigue. Today we're going to cover Method 1 for calculating fatigue, and this is a general method that is analogous to the basic procedure that we laid out in Chapter 3 of our Aerospace Strength Handbook, Volume 2. In that, we learned to handle a wide variety of fatigue problems, and we're going to follow the same approach to evaluate welds. There will be some minor changes. We'll identify those herein. Later, we will look at Part B of this lecture, which will provide another method for evaluating steels. So let's see how that works. So as we said, we're going to look first at Method 1, which is a general procedure which can be used to handle any weld fatigue analysis. So our first step in this procedure is going to be to evaluate what are our actual allowables of the material, what are basic static allowables. This is going to include FTU, it's going to include FSU, FTU if we have normal loads on the weld, FSU if we have shear loads on the weld. Sometimes we will also need FSY, and so many materials, if we are dealing with an aerospace material, we're going to have our handbook, Appendix E, which will provide the allowables for a number of materials, and this is based on MMPDS 9, which actually is a more comprehensive list of allowables, which is the one that we really should use in industry. In Aero 3261, we'll just base our analysis on Appendix E, and in industry, if you have, you can use that as kind of a baseline of what those allowables are. So if we have aerospace materials and we have the allowables in our appendix, then we will have both FSU and FTU for most materials we're going to deal with. However, if we deal with a non-aerospace material or a material that's used less than aerospace, like a civil engineering steel or something, it's possible we won't have as much information about the properties of the material. In that case, we may need to estimate our FSU, and we can do that with this little procedure here, just taking 67% of FSU, of FTU as our FSU. If we have a material that's used less than aerospace, then it's like a civil engineering steel or something, then it's very possible that we will have a lot less data on the strength of the material than we do in aerospace. In that case, we may only have FTU, and if that's the case, we can estimate FSU as the 67% of FTU as a general rule. Okay? All right. So once we have figured out what the FTU and FSU of our parent material is, that's the material that we're welding together, we then need to figure out what the allowable is for our electrode. Now, if we're dealing with a steel material, then we're going to call out the electrodes using a system developed by the American Weld Society, which basically calls out an E whatever, where that whatever is an indicator which includes roughly the tensile strength of the weld. So an E60 weld is 62 KSI FTU, a E90 has a 90 KSI FTU, and so on. There's also yield tension allowables for those. So this is where we'll get the allowables for electrodes. We will get the allowables for our materials from our appendix or from other sources. Once we have these two pieces of data, we then can estimate our tension and shear strength of the joints as follows. So for steels, the American Weld Society says that if we are dealing with a tension load on a weld, we're going to look basically at the parent material strength, and we're going to take 60% of FTY. So 60% of FTY is the tensile allowable for any kind of steel that's governed by the American Weld Society. Now, while in aerospace we're not really governed by the American Weld Society, we're using the FAR regulations, so we sometimes can do some different things with test data. But the Weld Society provides a good background. Anytime we deal with welds, we'll follow their approach. Now, if we have shear on that weld, then we're going to follow another procedure, which basically says we're going to take the electrode tension ultimate strength, we're going to take 30% of that. And then we're going to take 40% of the FTY of the parent material, and we're going to take the minimum of those two values, and that will be our shear allowable. So our tension allowable is going to be 60% of FTY of the parent material. Our shear allowable is the minimum of 30% of the electrode tension allowable and 40% of the yield tension allowable of the parent material. Okay, so that's what we're going to use if we have a steel. Now, if we have other materials like a titanium or aluminum, then we're going to go to our appendix and we're going to find what the FTU and FSU, the FSY if needed, the FTY if needed, and we use that data for the parent material. Okay, now what we have to watch out for those materials is whether or not the material is reheat treated. So most of the alloys that we're going to use in aerospace are heat treated. They're either cold worked or heat treated or both. Sometimes titanium is used in its annealed form, but other times it's used in other cold work and heat treated forms that gives better properties. For aluminums, they're almost always heat treated, and we're dealing with them in aerospace. And when we weld the parts, that heating of the part, localized heat of the part, can remove the effect, the beneficial effect of that heat treating. So typically we're going to want to reheat treat those parts. This is especially true for aluminum. Okay, so if we're reheat treating the part after welding, we're going to assume that the property is basically full strength afterwards. This is assuming that this is a weldable material. Your handbook has a little bit of data on which materials are readily weldable. Mill handbook has more data on that. Okay. Now, if we aren't heat treated, if it's titanium and it's not heat treated, then basically we're going to assume that whatever cold working or heat treating benefits that we had is lost, and we will use the annealed strength. So that means regardless of what the original strength of the material is, at the weld and right vicinity, we're going to assume that the property is whatever we find in that annealed column of the titanium. Now, if we have an aluminum, unless we get other data, we're going to basically say those have to be reheat treated. Now, this may not be universally true, but you really shouldn't use the full properties, heat treated properties for aluminum, unless you have test data to verify that it's good and hasn't lost its strength, because generally welds will cause that to lose its strength. Okay? And now sometimes with aerospace materials, somebody will go out and test them, and they'll say, and a good way to do this, let's say you've got a welded part and you don't really know what the allowables are and you can't afford to be too conservative, you want to be right on. You can go and make let's say a tension sample and a shear sample. You can make one without a weld and another one with a weld. And you can test both side by side, say 7+ samples per type of loading. And then what you can do is develop a knockdown factor. If you have the unwelded material has a certain strength and the welded material has the same or better, then you say there's no loss of strength. If the welded material has a loss of strength, you can come up with what factor of strength you have and use that. If that data is available, and like say the problem in a Aero 3271 problem says that we have, say, a titanium that has 80% of its strength or 85% of its strength after welding, then we will just take the parent material properties from the appendix, and then after welding, we'll just assume that that knockdown applies and estimate our allowable after with that. Okay, does that make sense? Okay, so that's going to be basically our approach. And basically, if our electrodes are chosen to be compatible with those materials, then these allowables, this approach, should hold. All right. So our first step is to get the allowables of the material. Once we have that, and we haven't done any fatigue analysis yet, we're just preparing to do our fatigue analysis, and our first step is getting these baseline allowables. Our next step is to figure out what the endurance limit is. This is going to be very similar to what we did in Chapter 3 of the Aerospace Strength Handbook. What we did there is we computed the pristine perfect endurance limit, S sub E prime, and then we used a number of Marin factors to take that perfect pristine endurance limit and turn it into something that's more realistic for our part. So once again, we're going to go back to section 3. We're going to look at table 3.4, and here we find what the pristine perfect endurance limit is. It's a factor of our FTU, and we're going to make sure that we don't use anything over what these max values are shown in the rightmost column, okay? So once we have our S of B prime, we then are going to apply a bunch of Marin factors to that pristine perfect value. We're going to start with our surface condition factor. We're going to assume that it is an as-forged kind of condition, so we're going to use K sub A with this equation here. We're going to use FTU to estimate what KA is. Our size factor, we're going to assume that's 1 because we're going to count for the size in another way. Our load factor, if we have a tension-loaded butt weld, we'll use 0.85, and if we have a shear-loaded butt weld or a fillet weld, we use KC equals 0.59, okay? Our temperature factor is going to be handled just like it was in Chapter 3. Regardless of whether we have a tension weld or a shear weld, we'll handle that the same way. So if there's a temperature applied, we can estimate our temperature the same way as we did back in Chapter 3 and get our K sub D. If there's no temperature applied, that KD is just 1. Our reliability factor we're going to use in the same way also. We're going to use table 343, which basically says, remember, when we looked at the S sub E versus FTU plot for some steels, and there are other materials that have a similar relationship, we found that we curve fit that, and we basically just did a curve fit to the average of the data, which means that this approach will give you a 50% reliability. If you want a higher reliability, we will use one of these reliability factors. So if there's a higher reliability required than 50%, then we will come here to calculate what the K sub E is. We then can use all these Marin factors to estimate what the real endurance limit is. This is done for you. If we have a butt weld loaded in tension, then we have this formula. We plugged in the 0.85 and we've got our KADE and our S sub E prime. If we have a shear loaded butt weld or a fillet weld, we will use this form of the equation, which has the 0.59 plugged in. Okay? This is how we estimate our endurance limit. Now we're going to add this little SSE to say that that endurance limit is applying to shear loads. Okay. So now we have the allowables of the material, and we've used some of those allowables to estimate our S sub B. Okay? Our next step is to figure out what our stress concentration factor is. Welds have stress concentrations. Our first one is a butt weld. If we have a butt weld, and remember, whenever we weld parts, we're going to get reinforcement or a little bit of extra weld. Looks like a little bubble on the part, a little slop. It's called reinforcement. If the reinforcement is removed by grinding or sanding or whatever, then that is better for fatigue, and we'll use a stress concentration factor, a fatigue stress concentration factor of 1.0, which means there's no stress concentration. Now remember, these stress concentration factors are actually the fatigue stress concentration factors, which means that they're both the theoretical and they include the notch sensitivity effects already, okay? Now, if we have a butt weld and the reinforcement is not removed, that doesn't mean we've added reinforcement. It means that when the weld was made, there's no call out to say remove whatever extra stuff is at the weld. That means it has reinforcement. We're going to use a stress concentration factor of 1.2. Now, for fillet welds, we're generally going to be using this 2.7. But you'll notice if you have a fillet weld and it's loaded perpendicular to the weld such that the toe, which means if you look at a little foot, and in the little toe of the weld right there, it's pulling perpendicular to that, so it's pulling on the toe, we're going to call that is at the toe of a transverse weld, and then the stress concentration factor is 1.5. If we have a loading that's parallel to the weld, parallel to the length of the weld, what happens is the end of the weld tends to get most of the load transferring in and out. So you get a much higher stress concentration factor. So we're going to use 2.7 for that, okay? All right, now if you look at a real welded joint, for example, these two plates welded together with 3 fillet welds, you'll notice with like a moment and a shear, you'll notice each of these welds has components that are both perpendicular and parallel. In this case, we'll just make it simple by taking the conservative 2.7 stress concentration factor for the entire pattern. It's nice and simple, okay? Got that? But if we have like a really simple loading and we can see, oh yeah, this is perpendicular to the toe, then we'll use the 1.5. Okay. So now we know what our endurance limit is, what our allowables are, and we know what stress concentration factors to use. The next thing we need to do is characterize our stresses. Now remember, What we need to do to evaluate fatigue is we're going to need to know to estimate the fully reversed stress level. If it's for normal loads, it's the fully reversed normal stress, and for shear loads, it'll be the fully reversed shear stress, which means it's going from positive, from one shear value to exactly the opposite, plus, minus, or shear going this way to shear going this way, up and down, right? That would be, if you go from the same value, positive and negative, that's a fully reversed value. If you have a fully reversed stress already, we can kind of skip this step because we don't need to characterize our stress because we already know what it is. However, if we have any other stress state, like let's say we're going from some high stress to some lower stress, or from positive to negative, but they're not equal and opposite, then that is a general stress. And in that case, we're going to have to compute what the equivalent fully reversed stress level is, and what we're going to need is the mean and alternating stress to do that conversion. Okay? So our first step here, characterizing our stresses, will be just identifying, yes, I already have a fully reversed stress, or no, I don't, so I'm going to calculate the mean and alternating stress. Okay? So we're going to do this in the same way we did back in chapter 3. Let's say we have a tension-loaded butt weld. If that's the case, we're basically going to use chapter 3 for everything. If we have repeated stress, if it's a fully reversed repeated stress, then we don't need to characterize our stress. We already said that. We'll just apply K sub F to that, and now we'll use that stress as our factored fully reversed stress. Okay? If it is not a fully reversed stress, then we need to convert it to one, and first step will be to calculate our mean and alternating components. So what we will do is go back to equations 3, 6, 1, and 2 from chapter 3 of our handbook to calculate the mean and alternating stresses. Now, if we have a shear-loaded butt weld, or any fillet weld, because we always pretend that fillet welds are loaded in shear, right? Then we do the same procedure. If we have a fully reversed shear stress going from positive to negative, the same shear value, we'll call that tau rev, and then we don't need to convert it, we'll just apply our stress concentration factor to it and use that. However, if it's not already fully reversed, then we will calculate the mean and alternating components using these two equations, which are analogous to what we saw in chapter 3. Basically, we're going to take the mean and the alternating and multiply them each by our stress concentration factor that we computed on the other slide. Okay? All right. Now we've characterized our stresses. We're ready to go and evaluate what is the equivalent fully reversed stress. But before we do that, now that we have the mean and alternating, we can actually evaluate infinite life first. Let's do that on the next slide. So if we want to find out what is the margin of safety against this part living forever and ever, hallelujah, then what we will do is we will need to plug into the appropriate equation. Now first, let's look at tension-loaded butt welds again. So it's normal stresses on a butt weld. If we have a fully reversed stress already, that means we've applied K sub F against our F rev, then we can evaluate the margin of safety directly by just taking the endurance limit divided by K times F rev minus 1. That gives us the margin of safety. Now, if it's not a fully reversed stress, then we will go back to chapter 3, and we have the equations for the Goodman equation, for the ASME elliptic equation, and for the Gerber equation, which will convert those mean and alternating stresses to fully reversed stresses. Now, since we already have that in our handbook in chapter 3, we won't repeat it here, but we will repeat it for shear loads, because that is not in that other equation. Even though it's very similar, we'll go ahead and provide it here. So if we have a shear-loaded butt weld or any fillet weld, once again, if it's already fully reversed stress, we can evaluate the margin of safety against fatigue, against infinite life, by just taking the endurance limit and dividing by the stress concentration factor multiplied by the fully reversed stress. If it's not already a fully reversed stress level, we would convert it. We have the Goodman criteria, the Gerber criteria, and the ASME elliptic criteria, and we will just plug in our tau A and tau M into these equations in order to evaluate what the margin of safety is. Now remember, these mean and alternating stresses already include the stress concentration factor. Okay? Now, you'll notice in the ASME elliptic equation, you need the FSY, which is not in our handbook. I did not repeat that in our Appendix E because we rarely use that in aerospace. However, Mill Handbook has that number for a number of materials, but what you can do if you don't have FSY information, you can always estimate it from FTU and FTY with this little formula down here on the lower right. Okay? So now we evaluated infinite life. Now if this passes, if you have a positive margin of safety, which means 0 or greater, then this means it will live forever. There's no need for additional work. If this margin of safety is negative, that doesn't mean that the part fails. All it means is the part won't live forever. Well, welcome to the club. None of us are going to live forever either, so that's not necessarily failure. Now, there are some parts, often fasteners, that we require infinite life for, mainly because we don't want to mess around with counting the number of cycles. But for many aerospace parts, they're designed for fewer than infinite life applications of loading, and so it may be acceptable with fewer. So if we fail this margin of safety, we may just need to do more analysis to evaluate how many cycles are we good for and how many cycles do we need to be good for. Okay? So our next step, once we've failed this check, if we fail this check, is to calculate our fully reversed stress level. Let's see how that works. So to evaluate our fully reversed, to estimate our fully reversed stress, what we're going to do is do the same thing we did in Chapter 3, and we're going to go and figure out which failure criterion we want to use. If we, for a tension-loaded butt weld, once again, we're going to go back to Chapter 3 and plug in our FA and FM into those equations to calculate FREV. If we have a shear-loaded butt weld or a fillet weld, then we will use these equations here for Gerber, Goodman, and ASME elliptic, which basically will convert the mean and alternating stresses that we have computed into fully reversed, equivalent fully reversed values, stress values. Now, once again, those mean and alternating stresses already include our stress concentration factor. Now, sometimes we often want to check for first cycle fatigue. So using Langer's criteria. Now, Langer's criteria isn't really a fatigue criteria at all. All it's doing, if you look at this carefully, you see this is just comparing the maximum stress to FSY. Okay? So if the maximum stress exceeds FSY, then we are going to expect to see yielding in the first cycle. In fact, we're going to see it in the second cycle and every other cycle after that. But it's called first cycle fatigue because it starts to yield at the first cycle. Now, even though this doesn't mean that we fail our fatigue check, what it does mean is if you're getting yielding in each and every cycle, it's very possible that your part will not behave as well as you think it is. So unless you develop the testing for this particular material, it's very possible that you're going to estimate something's good that may not be good. So you may need to look a little more closely. So this is what we use Langer's criteria for. In Aero 3271, we're not going to check Langer's criteria unless we're asked. If you're asked to check first cycle fatigue, that's what we're going to use. We're not going to use it as a fatigue criterion. Okay? So now we have characterized our stress into the fully reversed stress level. We're now ready to go back and remember the equation we looked at the SN diagram? That's what we're going to do next. So once we have that, we can evaluate what is the life of our part for anything other than infinite life parts. And we do that with the SN diagram, the stress versus number of cycles diagram on this log-log plot. So we're going to start by looking at this and we say, okay, on the vertical axis, we have our allowable stress. And what we're going to see, so if we have only a single application of load, we can expect that that part ought to be good for FSU. We're talking about shear load here, right? If we have tension load, we're going to go back to Chapter 3. If we have shear load, we're going to stay right here, okay? So if we have one cycle, we should be good for FSU. That's our first inflection point. The second inflection point says, okay, this is where it changes from low to high cycle fatigue. And for steels, this is at 1,000 cycles. And for other materials, it's close to 1,000 cycles. So we'll assume it's the same. And we're going to use that as FFTU, right? So we're going to, or excuse me, FFSU, because we're talking about shear loads here. So we're going to take our fatigue stress fraction, little f, and now Shigley provides a little curve for that, and we curve fit that, and we're applying that as our equation 338. So you're going to go to section equation 338, and you're going to calculate, if you have a steel, you're going to calculate your fatigue strength fraction. If you have any other material, we will assume that that fatigue stress fraction is 0.9. I believe that's conservative for many of the materials that we're going to use. And so we'll use that to define where this point is, okay? Our third point is here is at the endurance limit. And for steels, that's right at 1,000,000 cycles for many steels. So now for aluminums, it looks like aluminums don't have quite as solid of a point where they turn into infinite life. They tend to keep dropping, and that point where it goes to the endurance limit kind of number appears to be further right, like 10 to the 8th or 10 to the 10th or something for some materials that I've looked at. But we're going to go ahead and assume that this behaves the same as steel. It keeps it simple for us, and it should be conservative for most of what we're looking at. So we're going to assume at 1,000,000 cycles, our endurance limit is that point of inflection. Okay, so we have 3 points of inflection at 1 cycle, 1,000 cycles, and 1,000,000 cycles. Remember, we did the exact same thing with normal stresses in chapter 3. Now that we've done that, we're ready to calculate, to estimate what that curve looks like between our inflection points in these three ranges, our low cycle fatigue range, our high cycle fatigue range, and our infinite life range. Okay? So to estimate fatigue strength, there's two ways we can do this. We can go in here with a fully reversed, remember we only use fully reversed stresses on this chart. We can go in here with a fully reversed stress to estimate what the life is, or we can come out here for a number of cycles that we need and figure out what the allowable fully reversed stress level is. Okay? We're going to use these same relations, which basically show the shape of this semi-log curve. We've got the endurance strength is A n to the n, A n to the b, and our number of cycles is our fully reversed shear stress over our A to the 1 over B power. Okay, these are our two relations, same relations we use for normal stresses. We now will look at each range, where first we look at the low cycle fatigue range, and our coefficients for these two equations are shown here. This is our intercept and our slope of that equation. Okay, so now how do we know if we're in this range? Well, there's a few ways to do this. The easiest way is to take your fully reversed stress level and compare it to FSU times our strength fraction, little f. If our fully reversed stress is higher than FFSU, then that means we're in this low cycle fatigue range. If our fully reversed stress is lower than FFSU, then we're in the high cycle fatigue range. Okay? If so using that criterion, we then can go and use these two coefficients. So our two coefficients for low cycle fatigue are shown here. Now, if our fully reversed stress is lower than FFTU, then that means we're in the high cycle fatigue range as long as our fully reversed stress is higher than our endurance limit. In that case, this is our high cycle fatigue range. It's called finite life. These are our two coefficients. This is our intercept and our slope. And we'll use these and these fatigue strength relations to estimate the stress-life relationship. Now, if our fully reversed stress is equal to or less than our endurance limit, then we call that the infinite life range, because then our part should last forever. It should be cycling forever and ever into eternity. Now, I don't believe that any more than you believe that, but actually for all intents and purposes, that means it's going to survive long enough to where nobody's going to care anymore. Nobody needs to survive. It's going way beyond our practical experience. Okay? So that's how this thing works. So we've seen how to estimate our strengths and our stress concentration factor, how to characterize our stresses, how to turn them into a full reverse stress, and how to estimate our stress, fully reversed stress versus life relationship. And we've also learned how to evaluate the margin of safety is against infinite life. Okay? So if we just summarize our little procedure, we can do that right here. First, we're going to take a look at our fully reversed stress. We're going to compare it to our endurance limit. And if it's less than or equal to the endurance limit, our part will last forever. Live forever and ever. Okay? If it is higher than that, then we're going to check to find out. We're going to compare our F times FSU against our fully reversed stress to figure out whether this is high or low cycle fatigue. Now, if our fully reversed stress is equal to FF to SU, then we can use either the high cycle fatigue coefficients or low cycle fatigue coefficients with the same results. But if it's higher, we're going to need the low cycle. If it's lower, we're going to need the high cycle. Okay? All right. Then we compute our coefficients using the appropriate equations. We're going to then we can calculate either our fatigue strength or allowable for that number of cycles that we need, or we can calculate the number of cycles that we're good for that fully reversed stress level that we have using these two equations here. That's how it works. Now, all of this has been for a single stress. Now remember, this is a repeated stress, but it's a single stress level going from one value to another. And if it's that same stress level repeating over and over forever, that's called like a single stress state, right? Now, if we have different ones, like let's say it goes from 2,000 to 4,000 psi, and then it goes from 5,000 to 9,000 psi, and then it goes from +5 to -5, those are three different stress states. We're going to have to characterize each by itself and then combine them using Miner's rule to estimate the damage. We apply Miner's rule in the exact same way that we did back in chapter 3.8. You got that? So this is how we use method 1 to evaluate the fatigue strength of welds. This is a very general approach that can be used for a wide variety of welds, and it with careful practical analysis, it can provide good results for anything that we might encounter. Now stay tuned for the second part of the video looking at another method for evaluating fatigue life of steels.